Look good, no? Okay, I'm live. Yeah, thank you.
Yeah, you see, it looks very good.
Okay, is this getting static or whatever?
I'm testing it off my phone.
Oh, okay.
Oh, that's good. So, can you see it? Yeah, I can see it.
Getting static or whatever? My father is on the blue jeans.
Yeah.
Can you see him? Participants. Oh, that's Danny. When blue jeans create audio and video on. So they are saying they can see their video. I don't know what's happening there. Let's see. I don't know what's happening.
Your laptop.
Oh yeah. That is the laptop. How do you mute it? Okay. So I'll ask my father if they can hear me.
And then you may also want to. Yeah.
Hello, Dr. Saldana. There you go. One of the committee members is not at the moment, so I'm recording with multiple things.
Oh, you're recording?
So that you can see it.
You think you're good, Arka?
So can you see it on your phone?
Yeah.
Can you hear me also?
Yeah, I could hear.
And is it possible if you can check? Oh, so I'll share screen. Is this screen sharing on?
Screen sharing is on.
Okay.
But when you're ready, you gotta hit record.
Okay, let me record it anyway. So if I stop recording, what happens? I can start again. The screen.
Yeah.
So I can just say record on. Put this up because I want to check how I remove this thing. Okay. So you see, because some of the slides, this thing might be coming the way. Okay, right?
Yeah.
So look, one way
You can hide it.
Oh, is it? Okay. Ah, okay. You can see the slides on your.
Yeah.
Okay. Okay. Thank you, ma'am. I'll surely drop by later after all this.
Good luck. You got it, man. I'll start it.
I'm okay. Everything is on now. Everything is recorded.
I saw him and I was driving in and I saw him walking. And I
Okay. Everything, so we are recording by 3.5. So this is the camera also recording. Here you go. Where's the new? I have another thesis.
For somebody? I don't know.
Okay. Okay. So this one is recording.
Somebody going to adjust the lighting to make sure that your microgas is visible?
Okay.
Isn't there a
Is Dr. New? Okay, I'm starting to record. Ooh, look at that. Record is on. Share is on. Right. Everybody else on the beach.
So maybe we have missing.
It's not? Okay, is it?
Now I'm starting.
Great. Can you see if I'm standing here? You can see it? Do you see it?
This works for you. So we have scheduled, he's recording all of this conversation, discussion, and presentation, which you will have access to right after this. And we have scheduled.
Yes, it is.
Separate, with,
Okay.
with Chris. That's Dr. E.
Oh, okay, great.
Rick? Hey. Where do you want me? Oh, wherever, you sit up here. I'm sitting here. You sit up there. So you want to sit here? Go,
You're
ahead.
sitting.
That doesn't matter. No, I'm sitting here, but that doesn't matter. You sit, welcome to sit.
I'll sit wherever you tell me.
No, sit, please. Whatever.
Yeah.
Is it all?
So, so, do you think these lights have?
You don't want to be in the dark. You won't be able to. They won't be able to see you. I wish there was a way to adjust.
Only this thing? Okay, yeah.
What do you want to do? You have to wait for the next credit. You will have to remember the past 5 years. What do you want to do with the lighting? Unfortunately, I've only this bank of lights to go. Only the light, yeah, only this one, not that room.
Oh. So, one, okay, what about this? So this is the yellow light. So this one is the one.
Can you see?
So that's the YouTube one, and this one is recording whatever is live. You see the camera?
Can I still see you? All right, ready? Okay. Ooh, sorry. You okay? So, good morning, ladies and gentlemen. Welcome to Arkadeep Kumar's PhD defense. My name is Shreyas Melkot. I'm his advisor. I'd like to acknowledge the dissertation committee, Professor Rick New from Mechanical Engineering, Professor Stephen Danwick from Mechanical Engineering, Professor Chris Saldana from Mechanical Engineering, and the last member of the committee is Dr. Chris Arcona from San Goban Research Center up in Massachusetts. Unfortunately, he can't join us. He had a last-minute cancellation. So this presentation in defense has been recorded so that it's made available to him right after this defense is done. And then we have scheduled a one-on-one with him. Myself and Arka will participate in that this afternoon from 4 to 5 p.m. And then Arka will share whatever feedback he had with the rest of the committee after that is done. So it gives me pleasure to introduce Arka. He's been working hard and diligently for the last 5 years, trying to get to this point. It's obviously an important milestone in a graduate student's career. And so, just a brief introduction to Arka. Arka got his undergraduate degree in mechanical engineering from Jadavpur University in India, and came over as a direct PhD student. So it's taken him a little longer than a typical master's student would take to get to this point, but nevertheless, that's understandable. And he's been working in this area of sawing of silicon for photovoltaic applications since he started. Arka is looking forward to, notwithstanding some of the mishaps he's had, as far as his health is concerned, that some of you know, he's looking good today, and is all ready to go on to move forward with his professional career. He has accepted the ITRI Rosenfeld Fellowship with Lawrence Berkeley National Labs, and he will start next month if all goes smoothly here. And then that's what he's going to be doing for the next couple of years, as a postdoctoral fellow. So without further ado, I'll turn it over to Arka. In terms of logistics, I've advised him to keep his presentation to about 45 minutes. And then if there are burning questions, feel free to interrupt and ask him that question. If there are detailed discussion type of questions, please reserve it to the end of this presentation, and then we'll have an open session, and then depending on the committee's preference, we might have a closed session as well. All right, Arka, it's all yours.
Thank you so much, Dr. Melkot, for the very kind introduction. And so, in the interest of time, I'll start with the presentation. So welcome everyone to my PhD defense presentation on the fundamental investigations of surface and subsurface damage and wear in diamond wire sawing of silicon. As outline of the whole presentation, first I'll introduce diamond wire sawing process, which is used to manufacture silicon wafers for photovoltaic applications, solar cells. I'll talk briefly about the challenges faced in this diamond wire sawing process currently, which will help us motivate the research objectives to address those challenges, and then talk about the research tasks and findings which we have found throughout my PhD research. And then I'll conclude and mention the contributions to the field done by this PhD thesis. Now, the case of this PhD thesis is motivated by affordable solar cells. The DOE Sunshot initiative aims to reduce the cost of solar cells to make it more affordable compared to conventional sources of energy like coal or gas. As you see here, a graph which predicts the cost of solar cells to reduce to less than 10 cents per kilowatt hour, which is the parity with coal, and even less than that, like 5 cents per kilowatt hour in 2030, a few years. Now, to reduce the cost of solar cells, we have to see where we can reduce the cost more significantly. 30% of the cost comes from the substrate of solar cells, which are the silicon wafers. And we can reduce the thickness of the silicon wafers, which can save some material and hence reduce the cost. However, reducing the thickness of silicon wafers from 200 micrometers, which is the current state of the art, or about 180 micrometers over the years I've been doing PhD, to 100 microns, which is the goal of DOE Sunshot, we also have to make them stronger. Otherwise, the solar cells will break, as you see here. This is a complete solar cell, whereas this one is a broken one. And I'll pass out one complete solar cell, another broken one, for you to just look around. And these solar cells are breaking because of the micro cracks created in the surface and the subsurface of the silicon wafers, created during the abrasive slicing process of these wafers. Which brings to us to the next slide on the manufacturing process of silicon wafers for solar cells. It all starts with silica, which is like sand, which is molten in crucibles and then pulled out of the melt by a process called Czochralski process for monocrystalline silicon, as shown here, an ingot being pulled out from the melt from a seed crystal, or they're cast into ingots for multicrystalline silicon. Now, both this mono and multicrystalline silicon are then sliced by an abrasive wire sawing process, which consists of tiny diamond abrasives attached to the steel wire using nickel coating. As you see here, these are 10 to 20 micron size abrasives attached to the steel wire. The wire is running at a very high speed, 10 to 15 meters per second on these two rollers, whereas the silicon ingot is going down at a very slow speed, less than a millimeter per minute. And this relative motion between the silicon and the diamond abrasives on the wire slices the whole ingot into multiple wafers, as we see here. Now, my PhD thesis topic is concentrating on this part where diamond abrasives on the wire interacts with the silicon ingot to cut them or slice them into thin wafers. This could be simulated in our lab scale experiments with the scribing or scratching process, because that's how the abrasives on the wire, as they are traveling through the wire, is removing silicon from the ingot and slicing them into thin wafers. To complete the story of solar cells, the wafers are further processed into solar cells through etching, doping, giving an anti-reflective silicon nitride coating, which makes it look blue as the solar cell which is passed around with you. And then the solar cells are put into modules, which goes on our rooftops to give us energy. Now, to look into the challenges in the current state of the art of diamond wire sawing, one of the prime challenges is the abrasive slicing process, creating micro cracks in the surface and subsurface of the silicon wafers. Here you see the surface of the silicon wafers, a lot of scratch marks going from left to right, and there are these cracks, which you see here. These cracks can propagate when the silicon wafers are processed into solar cells with those processes like etching to remove surface damage, then doping, handling of these wafers to make them into solar cells, putting them into modules, or even during usage. When they're on our rooftops, there's thermal expansion going on, hailstorms, etc. And these break more easily because of these micro cracks. The micro cracks are also on the subsurface, as you see here. This is a FIB cross-section of the subsurface. The top part is the surface, this one is the subsurface, and you see here the micro cracks. In the interest of seeing the images better, I'll put the lights off, and you can see more clearly the micro cracks on the subsurface. The next challenge in diamond wire sawing of silicon wafers is cutting of multi-crystalline silicon. Now, compared to monocrystalline silicon, the cost of multi-crystalline silicon is much lower because it could be cast very easily, does not require a very slow Czochralski process of pulling out a crystal from the melt. But multi-crystalline silicon is characterized by many grain boundaries, twin boundaries, inclusions, dislocations, and whatnot. Not a very pure material compared to monocrystalline silicon. One of the prime challenges in cutting multi-crystalline silicon is lower manufacturing yield, which means if you cut 100 wafers for multi-crystalline silicon, maybe 20 or 30 will go to waste because they break while cutting. Whereas for monocrystalline silicon, the manufacturing yield is much more. Maybe 5 or 10 wafers would go to waste. And secondly, more critically, for manufacturers who are cutting the silicon wafers, there is greater consumption of the expensive diamond wire when cutting multi-crystalline silicon compared to cutting monocrystalline silicon. So to address these challenges, we first look into what are the prior work done and the open issues. So one way of reducing the micro cracks in the surface and the subsurface of the silicon wafers is using ductile regime machining. And this has been looked into by many people in the past, starting from 1980s and 90s for ductile regime grinding by Dow, Biffan, and Scattergood, and even using nanometric depth of cut, meaning the depth of material removed in each pass to be very small in nanometers, so that the stresses are not as high or microcracks are not formed. However, we saw in the prior work there is no investigations on the effect of actual abrasive shapes on the diamond wire, and there is no work in prior literature on the effect of cutting fluid on the ductile mode material removal of silicon. Cutting fluid we use in machining for coolant or removing chips, lubrication. However, for cutting fluid in diamond wire sawing process, nobody had looked into if the cutting fluid could at all affect the material removal mechanism, being ductile or brittle, and thus reduce the micro cracks. There are some prior work done in our group about the effect of abrasive shape using idealized shaped indenters, as shown here, which could be conical or rounded, but no work had been done on the effect of actual abrasive grid shapes on the industrial grade diamond wire, which is what I'm doing in my PhD thesis. Moving on to the next challenge, which is on the effect of multi-crystalline silicon material. As I was speaking earlier, multi-crystalline silicon has a lot of rings and twin boundaries, as well as carbides and nitrides as inclusions. And there are some work on the effect of this carbide and nitride inclusions done by Wu et al., but they found if there is a silicon nitride rod here or silicon carbide filament here, and they scribe across that impurity or those carbide and nitride inclusions, there is an increase in forces. And that could affect the cutting of multi-crystalline silicon. There could be more micro cracks, and that could mean the silicon wafers, which are multi-crystalline, when cut, might have more micro cracks compared to monocrystalline silicon. And that explains why some of the multi-crystalline silicon wafers break more easily compared to monocrystalline silicon. Moreover, some work had been done on the dislocation at the grain boundaries and at other parts of multi-crystalline silicon. And we know from prior literature that dislocations affect the ductile flow of material and how they could affect the cutting of multi-crystalline silicon. However, there is no systematic work done on the effect of grains and twin boundaries in multi-crystalline silicon when scribing or cutting by diamond wire sawing. So in my PhD thesis, I look into this aspect of cutting multi-crystalline silicon by doing scribing experiments across grains and twin boundaries systematically. Moving on to the next challenge, which is the wear of diamond. Diamond wire sawing is a relatively newer process compared to the loose abrasive slurry sawing. And the wear of diamond in this diamond wire sawing had not been looked into. Most of the prior work had been in diamond turning experiments like ultra precision machining for making lenses. And here you see some work which shows the wear of the diamond tool used in turning experiments. But the effect of wear of the diamond on the actual diamond wire on the silicon wafers had not been looked into. So in my PhD, I look into the effect of diamond wear on the silicon wafer surface and subsurface damage. That again relates back to the first challenge, which is the micro cracks on the surface and subsurface, which in turn affects the fracture strength of this wafer and are a major hurdle towards going to thinner wafers, saving material, and reducing the cost of silicon wafers for solar cells. Secondly, about the wear of diamond, we found from our industrial collaborators one of the major challenges in cutting multi-crystalline silicon is greater consumption of the expensive fixed abrasive diamond wire compared when cutting multi-crystalline silicon compared to cutting monocrystalline silicon. And there has been no work in prior literature about the reasons why the wear of diamond is more when cutting multi-crystalline silicon compared to monocrystalline silicon. So that forms one of my major tasks in the thesis. Now, this gives us the research objectives based on our literature review, and we see the limitations of prior work. The first research objective is to understand the effect of actual abrasive grid shapes on the diamond wire on the surface and subsurface damage in both mono and multi-crystalline silicon. The second is to understand the effect of multi-crystalline silicon materials, grain and twin boundaries on, again, the surface and subsurface damage on the silicon wafers cut by diamond wire sawing process. Third, to understand the effect of abrasive wear on the surface and subsurface damage and hence the mechanical integrity of these wafers, which means the fracture strength of the wafers, how it differs with the wear of the diamond wire. Fifth, to find the effect of multi-crystalline silicon material on the wear of diamond. And this would address the question which we hear from our industrial collaborators, why there is greater consumption of the diamond wire when cutting multi-crystalline silicon compared to monocrystalline silicon. And finally, we also want to understand one of the unexplored aspects of cutting fluid, which is generally used as a coolant in commercial diamond wire sawing process, on the ductile versus brittle material removal mode in scribing experiments of diamond on silicon. Now, the research objectives help us to get the research task. So the first task corresponding to the first research objective is to analyze the effect of abrasive shape on surface and subsurface damage in diamond wire scribing experiments. I'll go to and explain diamond wire scribing in a few slides. The second task is to analyze the effect of grains and twin boundaries on the surface and subsurface damage, again in diamond wire scribing experiments, which simulate the actual wire sawing process used in industry. Third, to analyze the effect of abrasive wear on the surface and subsurface damage of the silicon wafers cut by this abrasive wire in industry. And fourth, to determine the effect of multi-crystalline silicon material on the wear of diamond compared to monocrystalline silicon. Why does multi-crystalline silicon have higher wear consumption compared to cutting monocrystalline silicon? And finally, to analyze the effect of the cutting fluid on the material removal mode in diamond wire scribing. Moving on to the first task, which is the effect of abrasive. As we revisit, the major challenge in diamond wire sawn silicon wafer are the mechanical strength, fracture strength, affected by the micro cracks on the surface, as seen here, as well as the subsurface. And the cutting tool here are the diamond abrasives of different shapes and sizes. We see from prior literature in indentation experiments or scribing with idealized shape indenters on brittle materials like glass, silica, and even silicon, that the different shape of the indenter would affect the stresses created below the indenter in the material differently. If it's a sharp-shaped indenter, there'll be a plastic zone near the contact region, and then there'll be a median crack and lateral crack formed during loading and unloading of the indenter. Whereas if we have a rounder shaped abrasive or rounder shaped indenter, like a spherical indenter, it will not create as much cracks, it will only create a plastic zone. So the shape of the indenter critically affects the stresses and hence the material removal mode, whether it is being ductile or brittle with cracks formed in the indentation and scribing process. But in this PhD thesis, I'm looking at the effect of actual abrasive grid shapes, which are not as idealized indenters. So let's look into that. The objective in this task is to find the effect of actual abrasive grid shapes on the diamond wire on the surface and subsurface damage during scribing of silicon using a diamond wire. So for the methodology here, we use diamond wire, which has different abrasive shapes. Some are round, some are very sharp, and some are in between. And we scribe on monocrystalline silicon material, which is of 100 orientation, and we scribe in 110 direction. We use increasing depth of cut scribes, which means we start by just engaging the wire with the silicon and then go deeper into the material. And we can see the ductile to brittle transition as the abrasive or the wire goes deeper into silicon. And that is termed as critical depth of cut. We can compare the different shape of the abrasives by comparing the different critical depth of cut which is expected to come out of the scribing experiments. Finally, we correlate the shape of abrasive with the stress generated in the material. As I was speaking earlier, the different shape of abrasive is expected to create different stresses and hence difference in ductile mode material removal or brittle mode material. We analyze the scribes and the grooves by seeing the surface morphology of the scribes using SEM. Then we find the critical depth of cut, which is depth of the groove at which the first crack appears by confocal microscopy. And finally, for the subsurface damage, we use a focused ion beam technique where you see here, there is a gallium ion beam which is used to mill the face perpendicular to a scribe. This is the scribing direction. And then we can view the milled surface, the cross section of the silicon under the scribe and find what is the damage in subsurface. Okay. So when we scribe silicon with the actual diamond wire, we have to note here in this experiment, we have to find the effect of each abrasive shape. Hence, we are holding a diamond wire with a fixture and scribing or translating the silicon block perpendicular to the wire. This is a difference from the actual wire sawing process where we are the silicon is being cut by the abrasive by translating the diamond wire parallel to the length of the wire. But in this experiment, we are to find the effect of each abrasive shape. We don't want the groove created by one abrasive shape to be superimposed by the groove created by another abrasive shape. We don't want any confounding effect, and that's why we are translating the silicon block perpendicular to the diamond wire. So each abrasive shape is creating a separate groove, which we can analyze and find the effect of each shape. We use increasing depth of cut scribe, as I was explaining before, so that we can find the ductile to brittle transition or the depth at which the first crack appears. And then we can compare the different shapes. So for this experiment, we take a piece of diamond wire, and I hand out 2 diamond wires. These are written as Saint-Gobain confidential, so everything remains in this room. Anyway, now, so this is the diamond wire we got from the manufacturer of the diamond wire, where you see these are the tiny abrasives attached to the wire with nickel coating. We put that diamond wire on this fixture, which I fabricated. I can hand out the fixture as well. So this is the fixture. And so as you see here, the wire is held between 2 tightly tensioned screws. So the wire is very rigid in place. It can act as an indenter and not fly about while I'm doing scribing perpendicular to the wire. There is a micro-milled groove here, which we cannot see in this image, which holds or supports the wire in place so that it doesn't move at all when we're scribing perpendicular to the wire. This fixture goes on this micro-milling setup, which is in our lab, where it is attached to this top attachment. The silicon block is below that, and silicon block is put with a base plate on a force sensor, the Kistler microdyne, and then the force sensor is put on a XYZ stage, which is controlled by a computer, and I can scribe with increasing depth of cut. Now, a typical scribe created by this process of increasing depth of cut would start from a point of contact, have a region of ductile material removal, and then transition into brittle fracture. And we find the critical depth of cut here where the first crack appears by the confocal microscope. Even deeper, there will be larger cracks, like chevron cracks here, and the width of the groove will increase because more amount of abrasive is interacting with silicon and removing material. Now, for the purpose of this presentation, we analyzed two representative grids out of many grids we analyzed. One we name as grid 1, and this is the tip here, which is very sharp compared to grid 2, which is more round compared to grid 1. You see a number of tips here, but when we take cross-sectional profile of this grids from the ductile region of the stripe, where it gives the imprint of the grid shape, we find grid 1 has more or less very sharp shape, whereas grid 2 has like this toothed structure, but if we fit envelope to it, it is more or less creating a more rounded grid shape compared to grid 1. Now, to analyze the results of these grid shapes, we see that grid 1 produced surface scribes here with more of radial and chevron cracks on one side of the groove. Compared to that, grid 2, which is more round in shape, produced horseshoe-shaped cracks which are within the groove. And this is more indicative of how scribing by spherical indenters on brittle material gives horseshoe-shaped cracks within the groove, as found in prior literature. So there is a distinct difference in the surface morphology of the scribes created by different shaped grids. If we see the subsurface damage by the FIB process, we find grid 1, which is a sharper abrasive shape, produces cracks at the subsurface, which are lateral cracks because they are starting from the bottom of the groove. This is the groove. And the cracks are starting from the bottom and then curling up upwards, and then they will chip off. Compared to that, the rounder shaped abrasives produced not as much subsurface cracks as shown here. So the rounder shaped abrasives produced cracks within the groove and smaller subsurface cracks overall. When we compared or correlated these results with whatever results we find in existing literature, we find that the stress produced by the indenter shape depends on the cotangent of the semi-apex angle alpha. So if this is the apex of the indenter, a larger alpha will happen for a rounder grid shape, and that will give a smaller value of cotangent of alpha and a smaller stress, which means when you compare the critical depth of cut produced by these abrasives at which the first crack appears, we found the rounder abrasive shape, which has a larger value of semi-apex angle alpha, produced a higher critical depth of cut. It went to a larger depth before the first crack appears because the stress produced by this abrasive in the silicon material was lower compared to the stress produced by the sharper abrasive. So the key findings and takeaways from this task was in wire scribing experiments, we find the sharper abrasive grid shapes produce radial chevron cracks at the sides of the groove, whereas the rounder shaped abrasives produce horseshoe-like surface cracks within the groove, and rounder abrasive grid shapes produce fewer surface and subsurface cracks overall and a higher critical depth of cut. Now, how do we take this result to the actual diamond wire sawing process? So the implication of this research is we can engineer the grid shapes by which we have more rounder shaped abrasives and reduce the subsurface and surface cracks in wafer slicing which can increase the strength of these wafers and thus reduce the thickness of these wafers, reducing the cost of solar cells. Moving on to the next slide, next task of the effect of multidistant silicon. I'll pass around multidistant silicon examples we have here, where you see there is a number of grains and grain boundaries. This is a blown up picture which shows it very clearly. Multidistant silicon compared to monocrystalline silicon, and I'll pass some monocrystalline silicon as well, which are scratched or scribed so that you can understand there's not much grain boundaries in there. These are the grain boundaries which you see here, and the straight lines are more like twin boundaries. Grains and twins are like crystallographic defects formed during the solidification process when nucleation occurs from the melt and different parts of the melt solidifies. Now, one of the challenges, as I was speaking earlier, in cutting of multidistant silicon are these grains and twin boundaries apart from silicon carbide, nitride inclusions, and dislocations, which affect the cutting of multidistant silicon wafers, leading to lower fracture strength of these wafers compared to monocrystalline silicon, and that leads to lower manufacturing yield. More wafers break when we are cutting multidistant silicon compared to cutting monocrystalline silicon. And the second challenge is greater consumption of the expensive diamond wire when cutting multidistant silicon compared to cutting monocrystalline silicon. Now, to address the first challenge here, we want to find the effect of grains and twin boundaries in multidistant silicon by diamond scribing experiments, where we want to find the surface and subsurface damage. So we are using the similar methodology here as the previous experiment, but one difference, we are scratching or scribing on multidistant silicon blocks using the diamond wire setup. And we scribe across the grain and twin boundaries. Do note, here we are not using increasing depth of cut scribes because our focus is not on the shape of abrasive or finding the critical depth of cut. Our focus is finding the effect of grain and twin boundaries, which is in the workpiece. So we are using constant depth of cut scribes. The depth across the different scribes are same. We analyze the surface morphology by SEM. We analyze the subsurface damage by FIB, and for the multidistant silicon material across the twin and grain boundaries, we find the fracture toughness using micro hardness indentation or Vickers indentation, where it indents with the indentation creates a diamond shape like this, where we also see cracks emanating from the corners. The crack length C is measured. The value of half of the diagonal of the indent is measured, and the C and A are parameters which goes into the equation with material properties like modulus of elasticity and hardness, and some factors which are constant to give the fracture toughness K1C. Fracture toughness of a material is the amount of energy going into the material before the first crack appears, or before any crack appears. So fracture toughness is a threshold to cracking, and this we'll see as one of the factors in deciding which part or across the grains and twin boundaries is having more cracks. Moving on, when we scribe across the twin and grain boundaries, we see the frequency of cracks changes abruptly across the boundary. Here we see on the left-hand side a twin boundary. We say this is a twin because with XRD experiments done in our MCF IEN with Walter here, and we found that the different orientations of the material across the twin boundary were 3-1-1. They were not different orientation. So this proved that this is a twin boundary. It is still a discontinuity in the material where things like dislocations would pile up. Now, when we compare the number of cracks per unit micron scribe length, as seen here and here for the two scribes, we see the number of cracks per unit distance of the scribe changes abruptly across the boundary. Here we see the number of cracks is much more compared to this side, and the same thing happens here for another grid shape. And the reason for that, we hypothesize, is because of the lower threshold to cracking for the material on the left-hand side, which is region 1, which has a lower fracture toughness compared to the material which is 311 but on region 2. And this we see is true even for grain boundary. This was like at another part of scribing across the twin and grain boundaries, where we found while scribing across this 111 grain and 331 grain separated by this grain boundary, the number of cracks per unit micron or the frequency of cracks was smaller here. On the right hand side, 331 gave a higher frequency or higher number of cracks per unit micron of the scribed length. And we found here also 331 had lower threshold or lower fracture toughness, means it's easier to crack 331 compared to 111. So this is what we are seeing at the vicinity of the grain boundaries, but what happens during the grain interiors? To do that, we look at the scribed morphology away from the grain boundary, like 250 micron away in 111 and 250 micron away in 331. And we find there is similar differences in the number of cracks per unit length in 111 and 331. 331 has more frequent cracks. And that trend continues about 500 micron away. However, the differences are starting to diminish. You can see now this one is also showing more frequency of cracks. And if we move like 1000 micron away from the grain boundary on two sides of the adjacent grains, 111 and 331, we see there's not as much differences in the surface morphology of the scribe, about 1000 micron away. So with these results and other results we found, these are representative, we found that the cracking behavior changed near the grain boundary, as we saw in the previous slide, but they become similar away from the boundary. And we hypothesized that the reasons for this are the mechanical properties being different at the discontinuity like grains and twin boundaries, which is creating the differences in the surface morphology or cracking frequency across the boundary. So the key findings or takeaways from this task was the cracking frequency is changing at the vicinity of the boundary, but the frequency in adjacent grains away from the boundary was similar. Now, what is the implication of this study? We can expect that discontinuities in multidistant silicon like grains and twin boundaries would influence the stresses on the abrasive and can influence wear, which is one of our burning questions and challenges in diamond wire sawing. With this, we'll segue with the next topic, which is the wear. For finding the effect of wear on the surface and subsurface damage of the silicon wafers, we'll revisit the diamond wire sawing process. So I had handed down the spool already. So you see those are the spools of wire, and the wire starts from the new wire spool and goes onto rollers, goes round and round, comes out through the used wire spool. So during the cutting process, a little bit of wire is introduced into the cutting zone, like 500 millimeter, and then there is a back movement of 495 millimeter. So there is a reciprocating motion, and that's why it's called sawing, in a pilgrim mode for cutting of the silicon ingot with the diamond wire. So each time the ingot on the left-hand side sees the wire, it is seeing wire which has not contacted as much silicon. We can term it as the new wire side. Whereas the other side of the ingot, which is seeing mostly wire after it has gone through a number of iterations or rotations on these two rollers, it is seeing wire which has seen a lot of silicon. So we can term it as used wire side. So if we compare an ingot like this, the left-hand side of the ingot will be the new wire side, seeing mostly new wire while cutting, whereas the other side of the ingot will be mostly used wire side. Now, to analyze the effect of wear of the diamond wire on the surface and subsurface damage of the sliced silicon wafers, we have to we use this methodology where we slice monocrystalline silicon ingot using diamond wire sawing process in industrial conditions, and this was done by our collaborator. And then we extract the wafers from the two different new wire side and the used wire side, two sides of the ingot, and also extract the wire sections corresponding to the different levels of wire. And then we analyze the surface morphology of these wafers using SEM. We analyze the phase of silicon using Raman spectroscopy. We find the surface roughness, if there is a difference between the two wafers from the new wire side and the used wire side. And we also find the subsurface damage using FIB, and that affects the fracture strength of these wafers, which is found by biaxial flexure by our industrial collaborator. So we revisit the wire which I handed down, and you could see it, you could feel it, there are abrasives on it. It looks like kite string with abrasives on cotton string, but you cannot see them so closely with bare eyes. So the wire consists of a nickel coating holding these abrasives attached to them, and then they move over silicon and remove material by this scribing or scratching process. If you see the new wire, which we have the abrasives mostly intact in all their positions, and the abrasives are also having mostly intact shape. Compared to that, a used wire, which is from the used wire side, we found some of the abrasives is missing, or they are lost because they are pulled out during this cutting process. Some of the abrasives have chipped off, as you see here, this fractured diamond. Now, this means that the wear of abrasive is affecting the condition of the abrasive, and which will in turn affect the surface and subsurface damage of the silicon wafers it is cutting, and that in turn will affect the fracture strength of the wafers, which is what we are finding in the next few slides. When you compare the surface of the wafers cut by the two different wire levels, so we are extracting wafers from the new wire side and wafers from the used wire side, and if you just see the surface morphology of the wafers by SEM, qualitatively you can see there is a lot much chipping going on for the wafers cut from the new wire side, whereas the wafers cut from the used wire side shows mostly smooth surface. There are scratch marks and some intermittent chipping. And this was validated from our surface roughness measurement, where we found the wafers cut from the new wire side shows a lot of larger roughness and also a lot of scatter, which means there's a lot more chipping going on. Compared to the wafers cut from the used wire side, it shows a smaller roughness and more tighter distribution. So it's much more smooth. When he did Raman spectroscopy on this silicon wafers, we found that silicon, which is cut by the new wire side from the left side of the ingot, shows mostly silicon 1 peak, which is 520 centimeter inverse wave number, indicative of silicon in its pristine state of diamond cubic structure, meaning silicon is not undergoing as much phase transformation. It is remaining brittle, and that's what we see here, because there is a lot more micro cracks on the wafers from the new wire side. Compared to that, the Raman spectra on the wafers from the used wire side, for example, in many different points, this is just an indicative or representative spectra, we find there is silicon 1, so silicon is in the brittle state, but in addition to that, there is a lot more phase transformed silicon, and silicon is known to undergo stress-induced phase transformation at a critical stress value of 8 to 12 GPa. This has been found by prior work by other researchers, like Robertsi and all. And silicon goes from silicon 1 to beta-tin metastable phase, which is not found after the unloading happens, and then ends based on the rate of unloading as silicon 3, silicon 12, amorphous silicon, and different silicon phases. These silicon phases are more ductile. They are not as brittle. And that's what we see even on the surface, that the wafers cut from the used wire side has more ductile surface. So silicon is being removed like butter, not much brittle material removal taking place. So you might say, oh, this is great. We have with used wire, we have better wafers with smoother surface. This is what we want. We have reduced micro cracks. But there is a twist in the tail, which is the subsurface cracks. Here you see, before we go into the results, whenever there is a sliding of indenter, like diamond indenter on brittle material like silicon or glass, two types of cracks form. The median cracks, which are perpendicular to the surface, and they cause fracture in crack opening mode or mode 1 of fracture. And lateral cracks, which are starting from the bottom of the groove and then going upwards, and then if they reach the surface, they chip out. So these are the two types of cracks being formed on the surface, apart from radial and chevron cracks, which we saw in task 1, formed during scribing with different shaped abrasives. Now, if you see the subsurface of wafers cut by the new wire, we see there is some median cracks, but there is a lot more lateral cracks. And these are representative images of many, many sections investigated in the FID. So compared to the wafers cut by the new wire, which showed more lateral cracks, if we see the wafers cut by the used wire, we saw there is a lot more median cracks and not the curling upward lateral cracks. The median cracks here are not perpendicular to the surface because the abrasives are not idealized shaped indenter giving the load perpendicular. They are still median cracks which are a little oblique, but they are still more deep and they are expected to cause fracture of the silicon wafers at a lower stress level. And that's what we find in the fracture strength results, which was done by biaxial fracture by our collaborators. The fracture strength of the wafers cut by the used wire side had a lower value of fracture strength compared to the fracture strength of wafers cut by the new wire side. So the wafers cut by the used wire broke at a lower stress level. And the results were significant statistically, as we found out. The reason why this is happening, we hypothesize, is the different with where some of the abrasives are getting lost, as we see there, and the force on each abrasive is being uncontrolled. Some of the abrasives are getting very high forces, and because of that, there are median cracks being formed when the wafers are cut by the used wire side compared to wafers cut by the new wire side, and that causes more of median cracks compared to lateral cracks, which we see in the wafers cut by the new wire side. And that causes the fracture strength to be lower for the wafers cut by the used wire side. In summary, the key findings from this task was with wear of the abrasive, we see fractured and blunted abrasives, and even some of the abrasive pulled out or lost. And this affects the force per abrasive, as I was speaking in the previous slide. And the force per abrasive affects the micro cracks, being median cracks or lateral cracks. But when we see with wear, the wafers are formed with lower roughness and more ductile mode material removal because of stress-induced phase transformation of silicon. But that's just story only on the surface. If we literally dig deeper into the subsurface, we find the wafers are with median cracks when cut by the used wire. More median cracks than lateral cracks, which reduces the fracture strength of the wafers. Moving on to the effect of multi-crystalline silicon on the wear of diamond. So this task addresses the challenge why there is higher consumption of the expensive diamond wire using multi-crystalline silicon or cutting multi-crystalline silicon compared to monocrystalline silicon. To compare that, we revisit like multi-crystalline silicon having a lot more grains and twin boundaries, as we found in our previous task compared to monocrystalline silicon. And I'll pass out the two samples with the indenter which I used in this experiment. And you can see the scratches made across the grains and twin boundaries. We scribed multi-crystalline silicon and monocrystalline silicon with single tip diamond indenter. One example of that indenter is there in the sample passed around. And when we monitor the wear of the diamond due to multi-crystalline silicon and due to monocrystalline silicon, we analyze the scribing forces. If you remember in our setup, and I'll show it again, that we had force being measured with a force dynamometer. We analyze the surface morphology of the diamond here, not the silicon, because we are interested to find the wear of the abrasive diamond. Third, we find the radius of curvature of the tip of the diamond, how it is changing along with more scribing for multi-crystalline silicon and monocrystalline silicon, so that we can compare them quantitatively, the radius of curvature. And finally, we also do Raman spectroscopy on the diamond, not on silicon, to find if there are any stress-induced phase transformation of diamond. diamond also undergoes stress-induced phase transformation at very high stresses, and that's what we want to find if there is any phase transformation. So these are the two diamond-tipped indenters. These are SEM images, which are 120-degree apex angle. This is representative of the actual abrasive shapes which we found in the first task, and that's why these shape indenter was chosen. Now, these conical indenters are put in the scribing setup, and we are scribing on mono and multi-crystalline silicon. For monocrystalline silicon, we are using 100 orientation and scribing in 110 direction. Because in the actual wire sawing process for monocrystalline silicon, these are the main orientations of wafers cut of 100 orientation, and the cutting is happening in 110 direction. Now, the scribes are made non-overlapping so that each scribe is identical in everything. We are just monitoring how much the material is wearing the abrasive at a constant depth of cut of 10 micron. What that means is we engage the indenter by 10 micron depth and then scribe for 20 millimeter. And we repeat the scribes many, many times and monitor at regular intervals, stopping the experiment for both mono and multi-crystalline silicon, and then checking the surface morphology of the diamond, checking the radius of curvature of the diamond, how it is changing with wear. The scribing forces, here I plotted the resultant forces across all the scribes I did for multi-crystalline silicon and for monocrystalline silicon. We find that when you plot the box plot, with the average forces for multi-crystalline silicon is consistently higher compared to the average forces for monocrystalline silicon. And there is some scatter, there is some high forces, some low forces. Higher scribing forces is expected to create higher stresses on the abrasive, because here we are using same shape of the abrasive. So we can assume similar contact area between the abrasive and silicon. If the forces are higher with similar contact area, we can expect the stresses are higher if the forces are higher, which is for the case of multi-crystalline silicon. And we are hypothesizing that the multi-crystalline silicon is giving higher forces because of the discontinuities in multi-crystalline silicon, like grains and twin boundaries, and possibly also inclusions like silicon carbides and nitrides, which are entrained into the solidification of the melt during solidification of multi-crystalline silicon ingots. Moving on to the evolution of diamond wire, we find this is the condition of the abrasive at 0 millimeter, which is before scribing. As soon as we scribe for a distance of like 140 millimeter, we find the top of the diamond for the tool which is cutting multi-crystalline silicon has been blunted off. And this is similar to what we see in our actual wire sawing process, where we saw the own diamond had blunted. The tool for monocrystalline silicon develops some notches here on this side. If we move even for a higher scribing distance, like 200 millimeter of scribing, we find trenches are being developed in the tool for multi-crystalline silicon. Similar trenches or notches are also developed here for monocrystalline silicon. The tool scribing monocrystalline silicon. We move for more distance, like 260 millimeter, and we see the trenches are getting deeper. There is some Hackley fracture pattern taking place here. And then we scribed up to like 320 millimeter to just to make sure that we are seeing trends which are consistent over longer scribing distance. And if we analyze the fracture pattern which we see in this diamond due to multi-crystalline silicon and monocrystalline silicon, they're typical of diamond fracture as found in previous literature by Brian Lawn, Hull, and others, that diamond fractures through a Hackley fracture pattern as well as something called river pattern, where you see these lines, which is called the river pattern. And there is Hackley fracture pattern in both the indenters we found. And more importantly, if we compare the wear of diamond on the actual own wire in the previous task, we see similar blunting of abrasive, similar chipping, fracture of abrasive, similar river pattern. So our experiment is simulating the actual diamond wire sawing process. But that's very qualitative, right? We want to see some quantitative results. And for that, we find the radius of curvature of the tip using confocal microscopy. And here we are monitoring the radius of curvature for the tool scribing multi-crystalline silicon, which is the blue one, and the tool scribing monocrystalline silicon, which is the red one. Now both these diamond tips are having an increase in radius of curvature, which is expected because the diamond is varying. However, if you compare the rate of increase of the radius of curvature, the rate of increase is higher or more aggressive for the tool scribing multi-crystalline silicon. You see it's a higher slope compared to the tool scribing monocrystalline silicon. So as we are seeing, this is consistent with the story that the forces are higher in scribing multi-crystalline silicon using diamond wire, using diamond indenters, and that causes or are expected to cause higher stresses and more wear of the tool scribing multi-crystalline silicon compared to the tool scribing monocrystalline silicon. And I talked about doing Raman analysis to find the stresses in silicon. So diamond as a material has a Raman spectra of 1332 centimeter inverse peak, which is a pristine diamond peak. Diamond can phase transform into graphite and other phases, but for that it requires very high stresses and temperature. We did not find that in our experiments, even though some others have found limited graphitization in diamond wire sawing process. What we found that both the tools showed a peak, the blue one, before scribing at 1332 centimeter inverse. After scribing, both the peaks shifted to the right hand side to 1334.4 centimeter inverse for the tool scribing multi-crystalline silicon and 1334 centimeter inverse for the tool scribing monocrystalline silicon. So a shift of about 2 and 2.4 centimeter inverse. And this shift means there is compressive residual stresses created in the diamond due to the scribing process. If we look at prior literature about the peak shift of diamond for the residual stress, we find that about 1.625 centimeter inverse of peak shift happens per GP of residual stress. If we use that model and estimate the residual stresses created in this diamond abrasives, we find that the residual stress is about 1.4 GPa, compressive residual stress, for multi-crystalline silicon, the tool scribing multi-crystalline silicon, compared to the tool scribing monocrystalline silicon having about 1 GPa. Now this is happening because of the repeated loading of the abrasive during the scribing process, and it agrees with prior work by Yang, which talked about graphitization and phase transformation of silicon, and others. So the key findings from this task was the forces in scribing were higher for multi-crystalline silicon, and the wear of diamond is characterized by microfracture, mainly in the diamond wire sawing process, which we are simulating by our scratching process. The tip radius is increasing at a higher rate for multi-crystalline silicon compared to monocrystalline silicon, consistent with the higher forces we see for the multi-crystalline silicon scribing, and the Raman shift shows higher compressive stress. Moving on to the last task about the effect of cutting fluid. Now, cutting fluid in machining operations are used as coolant, as lubricant, and to take away chips. But here we are trying to find an unexplored aspect, which is if the cutting fluid could affect the ductile mode material removal of silicon. To do this, we scribe using again single point diamond tip indenters on monocrystalline silicon of 100 orientation and 110 direction, and we scribe under dry condition and then using the cutting fluid. The cutting fluid was supplied to us by our industrial collaborator. We analyzed the surface morphology of the scribe. The confocal microscopy is used to find the critical depth of cut, and we also use Raman spectroscopy to find the phase of silicon after scribing. So some prior work in this space had been done by Dr. Danley's group some time back, where they found that different liquids in contact with silicon, like ethanol and acetone, gave different wear rates of silicon when scribed under identical conditions of load and the same indenter. So fluids are known to have any effect on the material being scribed. Here we want to find that if the cutting fluid, which is actually used in industrial operation in industry, can have any effect on the ductile mode material removal. So we are simulating the wire sawing operation in industry by the scribing process, and in this experiment again we use the increasing depth of cut scribe because our objective is to find if using the cutting fluid gives a more ductile mode material removal compared to using dry conditions. So we want to compare the critical depth of cut, which is the depth at which the first crack appears. So this is a scriber, and this is a microelectronic grade single crystal silicon of 100 orientation, and we are scribing by flooding this zone with cutting fluid. And we also see here while we are scribing in dry conditions. Now, if we compare the scribes in using the fluid and using dry condition, we are starting from the same point here, using the fluid and using dry condition, and we see initially there is we don't see anything because it's ductile mode, and the light is all reflected. Compared to when the black part starts, there the fracture of silicon has occurred, and thus we see the line here. The average distance to transition over many scribes was higher when using the cutting fluid compared to when using dry condition. And if we take the confocal microscopy of the grooves to find the critical depth of cut at which the first crack appears, sometime here and somewhere here, we find the critical depth to be higher for using the cutting fluid compared to the dry conditions. If we compare the ACM images of the scribes after the same distance from the start of the scribe using the dry and using cutting fluid, here also we find that for the dry condition there are some cracks appearing on the side, as you see here, radial chevron cracks on surface. Whereas on the other one, we see that using the cutting fluid there is more ductile mode material removal, not as much cracks. If we analyze the Raman spectra of the silicon inside these grooves, for the dry conditions, we find again silicon of diamond cubic structure giving a 520 centimeter inverse peak, showing not much phase transformation is taking place. Compared to that, when the silicon is scribed using the cutting fluid, we see there is a lot more phase transformation like amorphous silicon, silicon 3, which allows silicon to be removed in ductile phase. To explain our findings, we take help of an effect called Rebinder's effect, which was found way back in 1920s, where they found that there's a reduction in hardness of rocks due to the adsorbed chemicals. This was revisited by Westwood in around 1960s, who correlated the zeta potential of the liquid in contact to maximum hardness. Zeta potential, to note, is the potential difference, electrostatic potential difference between the stern layer of liquid in contact with the solid and the bulk liquid solution. Now, Yost and Williams found that more negative zeta potential gives even lower hardness, and most negative zeta potential in the liquids they had investigated gave the most minimum hardness. And this reason why hardness is reduced by zeta potential is because zeta potential changes the near surface mobility of dislocations because of the surface charges created in electronic material like silicon, and that creates the reduction in hardness as the dislocations move. We found the zeta potential of the cutting fluid was more negative when we did zeta potential measurements of silicon ground powder suspended in the cutting fluid versus silicon zeta potential when put in water. Water is a proxy for the lab air, which is not very dry because there is always moisture in air. And we also found by Vickers hardness indentations that using the cutting fluid, the hardness is lower compared to using the dry conditions. So this explained our results that using the cutting fluid, we have a higher critical depth of cut, which means it promotes ductile mode material removal while using the cutting fluid. And the reason for that is the chemomechanical effect, decreasing the hardness and increasing the ductility of silicon. The key takeaway from here is we can possibly alter the chemistry of cutting fluid in future. We can soften silicon, reducing brittle fracture and promoting ductile mode material removal, and thus could speak to our challenges of reducing the micro cracks in the surface and subsurface of the soil silicon wafers. Moving on, to wrap up, I'll correlate what are the challenges, revisit them, and look at the research objectives which were motivated by the challenges, and talk about the key findings which have addressed those challenges. So the first challenge we mentioned was the micro cracks in surface and subsurface. And one of the ways of addressing that was the effect of the actual diamond abrasive shapes. We found that the rounder abrasive grid shapes reduce surface and subsurface cracks during the wire scribing experiments. Secondly, for the effect of micro cracks on surface and subsurface, which is one of the challenges, One of the research objectives was to find the effect of cutting fluid on the material removal mode being ductile or brittle. And we found using the cutting fluid and altering the chemistry of cutting fluid would promote more ductile mode material removal, thus reducing the micro cracks. The next challenge was cutting a multi-crystalline silicon because of the grain and twin boundaries, apart from other inclusions and carbides and nitrides, which was one of our research objectives, to find the effect of grain and twin boundaries. And we found that there is a difference in crack frequency in the vicinity of the boundaries, but the crack frequency becomes similar away from the boundary in adjacent grains. And the last challenge which we addressed was about the wear of diamond wire. And this was related with cutting a multi-crystalline silicon, that there was greater consumption of the diamond wire while cutting multi-crystalline silicon compared to monocrystalline silicon. And we found that multi-crystalline silicon shows higher forces and more wear of the diamond overall compared to scribing of monocrystalline silicon. And to address another challenge about the effect of wear of diamond wire on the silicon wafer surface and subsurface damage, we find that with wear, we have smoother surface, but median cracks in subsurface, which reduces the fracture strength of these wafers. So to revisit the major conclusions from the different tasks, we found that rounded abrasive shapes reduce the surface and subsurface damage in scribing of silicon. We found that the surface cracking changed across the boundary of grain and twin boundaries in the vicinity, but become similar away from the boundary. We found the wear of diamond, which yielded smoother wafers, but median cracks in subsurface and reduced the fracture strength of wafers. We found that the wear of diamond is more or higher when using multi-crystalline silicon scribing compared to scribing monocrystalline silicon. And finally, that cutting fluid chemistry would promote the ductile mode material removal of silicon. So the contributions of my PhD thesis was, which I found new in my research, was to find the effect of actual abrasive grid shapes on the diamond wire during slicing of silicon wafers on the surface and subsurface damage. We found the role of grain and twin boundaries with a systematic study in cutting of multi-crystalline silicon, which could affect the fracture strength of the wafers because of the micro cracks created in multi-crystalline silicon. We found the effect of wear of the diamond wire on the surface and subsurface damage, and hence the mechanical integrity and fracture strength of the wafers. We found the first reasons for the increased wear of multi-crystalline silicon while cutting multi-crystalline silicon, and could explain the increased wear consumption for cutting multi-crystalline silicon versus monocrystalline silicon. And finally, I found the effect of cutting fluid to promote ductile mode material removal of silicon. These are some journal publications, some are still submitted, and some conference proceedings. And with that, I'll end with acknowledging my PhD advisor, Dr. Shresh Melkor. Thank you for accepting me as a student and mentoring me throughout the years to make me better, raising the bar higher and higher, even till yesterday, and will continue even in future. Dr. Stephen Danlook, who had given me advice not only about research, but more about life. Dr. Rick New and Dr. Saldana for being available all the time for advice on my research. Dr. Chris Arcona, who is not another committee member, but will join me later. And Steffi Kaminsky at St. Gobain, who had critiqued my work and given me advice from their industrial collaboration point of view and given me the challenges they face. St. Gobain Northborough Research Center for funding my work in initial years, and then NSF Goli Grant for funding my later years of my PhD. My lab mates in past and present, many have graduated, and even now who have been very helpful to me for research and life overall, which brings to me my parents, Shipra and Ashish Kumar, who are there being the rock pillars of support from India, and they're right now on YouTube viewing this presentation. My friends here, who are my family, who have, gave me a hand every time I've fallen down, like recently with a fractured arm. They've given up their sleep to ensure mine, going to hospital and whatnot. Asha for Education community, which is a community I love and given me support beyond academic work at Georgia Tech. And finally, the Georgia Tech community, with all their services, making my presentations better, making my writing better, even Stinger it, taking me home late at night. With that, I'll thank everyone for your time and attention, and I'll take questions.
All right. Arka has taken fracture and damage to a different level by testing it on himself as well.
Yeah.
During the years. I know it's past the time that we had allocated, but nevertheless, I'd like to open it up for some questions from the audience before we restrict the questioning to the committee members. Yes.
Thanks for a great presentation. I think it went a little bit fast. There was one interesting slide where you were showing a twin boundary and then a very difference in the frequency of cracks from one side to the other. Can you talk about that just for 1 minute?
Sure. So one of the major challenges in cutting multi-crystalline silicon is because of these discontinuities, which are the Green-Sun twin boundaries. Now we are scribing in this particular task across the Green-Sun twin boundaries, which is just coming up here. Okay. So a twin boundary, a crystallographic twin happens when one layer of atoms displaces by a certain just one atomic distance. That's how a twin boundary happens compared to a green boundary. Now, so there is not much difference in there is no difference in the orientation as we found by XRD. Both are 311 grains. So they're expected to give the same fracture or same cracking frequency. However, we found that across the twin boundaries, the number of cracks or the per unit distance of scribe, that's what a metric I term as cracking frequency, the number of cracks per unit distance of scribe length, changes very abruptly across the boundary. That happened for multiple scribes, like only 2 are shown here. And the reason we see this is because of the fracture strength changing also abruptly across the boundary. We found the fracture strength by Vickers microhardness indentations to be lower on this region 1 of 311 grain, 1.03 MPa meter compared to region 2, which means region 1 had a lower threshold to fracture. Less energy has to be pumped in. That's what fracture toughness is. How much energy going into the material before the fracture occurs. So less energy has to be pumped in before fracture occurs in region 1 compared to region 2. Now, why this is happening is most likely, which we are hypothesizing, that the material properties across the boundary are different, because any boundary in multi-crystalline silicon is a discontinuity, where things like dislocations can pile up, inclusions can come and just stay there because they cannot cross that boundary during the solidification process at different stages of solidification.
Other questions? Yes.
I had a quick question on the Raman you showed on the diamond tip itself.
Oh, okay.
It was interesting to see the peak getting narrower. It seems like the diamond might be getting more ordered.
So that's the full wave half max which you are speaking. And I did look into diamond full wave half max. You're right that it is getting narrow. It's not. So if diamond goes into graphite, there is a lot more difference in the full wave half max. But we are not seeing graphite here. I mean, the change in the peak shift is only 2 centimeter inverse, whereas graphite is 1334 to like more 1350 is one of the graphite peaks. When you say it's become more narrow, the diamond might be getting more ordered. That's what, and that might be because of the compressive residual stresses happening as the diamond is scribing across silicon. I mean, I understand the lattice is getting deformed. That's why the Raman spectra is getting more ordered. So most likely it is because of the compressive stresses happening. And that's what we also find from the residual stresses having a rightward shift, which is compressive residual stress. So I think that is consistent with what you are saying, that full wave half max is becoming narrower.
Are the residual stresses large enough to deform the crystal lattice
So
that you estimate?
Now, the reason we are seeing residual stresses, thank you for this question. This is one opportunity for me to explain residual stresses, why it is happening. So whenever we are stressing a material, if it is elastic, it comes back and there is no residual stress. Only if a material undergoes some plastic deformation and the material cannot spring back to the final, the initial form, will have some residual stresses. the fact that we are seeing here a peak shift indicates that the stresses are large enough to create some plastic deformation, and the material doesn't come back to the same phase or same structure as before. So there is some lattice deformation taking place, and that's why we see the residual stresses by the peak shift. If there are no residual stresses or no lattice being deformed, we would have not seen the peak shift.
Any other questions from the audience? Okay, go ahead. Yes.
So you said that if you use cutting fluid, then there's more plastic formation and it's easier to cut and then less cracks. But does it have any implication on final use of silicon wafer because you have changed the chemical composition of the surface?
That's again a great question. So the cutting fluid I used in my experiments were supplied by the industrial collaborator, and they already use it in their process. We just wanted to find if there is an effect of cutting fluid apart from cooling and lubrication, which is the general use of cutting fluid, on the mode of material removal being ductile. So they're already using it, and they're cleaning the surface later on by some method.
All right, in the interest of the committee's time, I will curtail further general questioning. You're welcome to talk to Arka after his defense is done. If you're going to leave, please leave quietly. If you want to stay, as long as the committee is okay with it, you can stay. But if you're leaving, please leave quietly. We'll give Arka a minute or two while those of you are leaving leave. We'll start the questioning from the committee.
Yes, that is
Would you like to start?
Sure. Yeah. So task 5, you talked about the effect of cutting fluid.
Yes.
And you came up with an explanation, but I wondered, did you explore other possible explanations? Because two things came in mind as I was looking at those results. One is that with the fluid, as you traverse, it's going to see higher loads before you reach the transition, because and in fact, your Raman measurements show that you got an appearance very similar to the higher loads, and that's going to influence things. Yeah, that one. And then the other was the fluid reduces friction in some way, right? And that's not discussed at all. I mean, how do you rule out all these other possible explanations and conclude that it's this chemo-mechanical effect?
So about friction, that is the first thing which comes to mind while using cutting fluid, because it's known to reduce friction in other forms, right, in machining operations. We found that the friction coefficient does not change as significantly, because this cutting fluid, to note, is a water-based cutting fluid, which means it's chemicals which are proprietary, so they don't tell us what it is, but it's mostly sodium and potassium hydroxide or some salts of it. And they sent me a concentrated chemical which I measured like 97 ml to 3 ml. So it's mostly water and with some of those ions like sodium, potassium. The friction coefficient did not change as much using the cutting fluid and in dry conditions. So I had thought about that as the first reason. Even Dr. Vandenberg also talked with me about this, friction being a factor. So we thought there might be other reasons for the ductile mode machining,
Yeah.
which we find here.
Just one comment before you go. You didn't mention that in your dissertation document.
Oh, okay, I see.
In fact, I did a word search on friction. You never use the word friction anywhere, so it doesn't appear.
Okay, I'll mention this.
But if you did do
Yeah.
those measurements, then
Right.
that's important. I think that's an important.
How do you, can you say something about how you actually computed or estimated the friction coefficients?
Sure. So the friction coefficient was found by taking in all these experiments, we have the force dynamometer capturing the forces. So we have the tangential force and the normal force, and we take the average. Sorry, not average. We take the normal force by tangential force to get mu, which is the friction coefficient.
Right.
This using the cutting fluid. Sorry.
Normal over tangent.
Okay, sorry, the opposite way. Tangential over normal. And that's how we found the friction to be remaining almost same for
Over the two cases.
two cases, not as significant over the different experiments. Like there might be some difference, but not statistically as different. Then about changing stresses with the liquid.
Well, with the fluid, because you have the fluid, is it supporting some hydrostatic
Static
pressure?
pressure.
So you get a distribution of the pressure versus the dry. You might not get such a distribution. I'm just.
That's one
looking at what the
possibility,
rubric-
surely.
If it's changing in other words, the effective profile or something.
Or effective stress state. That's what on the slide.
Which,
Yeah.
which would affect the stress
Stress
state.
state,
Yeah.
yeah. So, I mean, that would involve. I see what you're saying when using cutting fluid. This is similar to, I guess, hydrodynamic lubrication or etc., where the fluid takes a number of load, right? But then there is a fluid film which is thick enough to take the load between the shaft and the bearing.
Mm-hmm.
Here, the cutting fluid primarily is providing an atmosphere on which we are doing the scribing. The diamond is still getting in contact with silicon. Maybe the fluid film is not as thick to take that much load or change the thickness. So my analysis is based on the fact that whether the cutting fluid, just like in previous work by Dr. Danluk and others, it is showing some change in the surface characteristics, changing some dislocation dynamics or due to surface charges created in an electronic material like silicon. That is affecting how silicon is becoming more ductile or reducing the hardness, because if dislocations move more readily, it is becoming softer.
But that's your hypothesis.
That's a hypothesis.
Dislocations move.
That's a hypothesis.
Yeah.
Now, the question which you're saying about if fluid film is indeed changing the stresses, I feel that the configuration here with the indenter getting in touch with the abrasive and then creating, indenter getting in touch with silicon and then creating the scribe, it is in very close contact between the diamond and silicon, and the fluid film thickness may not be as much to create a change in stress, or some stress is taken by the fluid. That hypothesis may not apply in this case.
That's still your hypothesis.
That's
Definitely not applied.
Yeah.
Because you haven't tested
I have.
the fact that is there a fluid film that is bearing some of that load and thereby reducing. That could potentially be the reason for why when your hardness is lower. One could argue, I guess.
Right. So the question is, your hypothesis is that the fluid is changing the properties of the material, whereas it's not affecting the way the load's being applied to the material.
It could be also affecting the load of the material, but
So the way you're applying the load, is that any different for the two cases with and without fluid?
no,
Right.
they're identical. So my hypothesis is the material is getting changed because if we see the surface at constant travel distance after the start of the scribe, or if we see the Raman spectra as well, we see there is more softening or ductile mode, and also the Vickers hardness indentation which you're seeing. which means chemically there is some changes taking place.
When you do that Vickers hardness, do you do it, so you put the liquid on, you just do the indent?
You flood it.
You flood it?
I flood it.
Okay.
I mean, this was the scribing, but in Vickers also you flood it.
Is there a difference in the depth of the indent with and without the fluid? Do
So,
you see a difference in the depth of the indent with and without the fluid?
so here's the thing. That could be readily seen from these results. The confocal microscopy gave the depth of the groove at this point for using the fluid, and at this point using the dry conditions. And the depth is higher, right?
The Vickers indent.
Because indent is what I'm talking about.
Yeah.
So that is,
Because this could be, just building on Dr. Neal's question, it's a possibility that if indeed the fluid is taking up some of the load, bearing some of the load, it takes much greater load for you to break through that film to actually initiate fracture. And that could explain this result, potentially.
right. But I'll build on what you just said, which is one of the possible ways in which we can address this question, is if the depth of cut is same or almost similar at like the same depth.
Was it the same? That's the question.
Now,
Because
the depth of cut was measured at the critical depth of cut, which is ductile to critical transition. But if we compare, so these are possibly in the same depths because they are at the same travel distance. So we are using same increase of depth. So 5 micron depth of increase over 5 millimeter. That's the scribe used. And so in one case here, so they're expected to create the same depth because we are using the same machine condition. But in one case here, we see there's not much cracks formed.
yeah, but the question really is
The depth.
if you were indenting, forget about scribe, if you're just indenting,
Yeah.
and with and without fluid, if indeed the fluid is bearing some of the load, then I would expect the depth of that indent, even if you're applying the same travel distance,
Right.
You're applying a certain load. The depth of that indent would be different if indeed the fluid is bearing some flow. Load. So did you notice any difference in the actual indentation itself?
So the indenter in here we have is programmed to depth at a programmed to indent at a constant load. We don't compare the depth, but what you're saying is comparing the indent depth.
Yes.
And that is fine. But we have to also remember, Dr. Malkot, here we are simulating the scribing process and not indentation, because the actual wire sawing process is a scribing process. So there will be always dynamics of a thing moving over another, which means indentation might not be a right.
The reason
Without fault, yeah, we're just referring to the Vickers micro hardness. You said
Right.
with the cutting fluid,
Yeah.
it's less. Okay.
It's less.
And so you're attributing that to the material softer, but could it be less because there's fluid entrapped and you're going to a fixed load,
Right.
and so
some of that load is
some of that load is being carried by that fluid. In there.
So the process in which we find the Vickers hardness is by that formulation which I showed as the indent. It's based on the cracks being formed. So the Vickers hardness was found by
it's the hardness, right? You're not measuring the toughness.
no,
Yeah.
but yeah. But right. But the hardness is also measured directly with the empirical formula they have in the machine.
Yeah, but that empirical form is looking at the indent size.
Right.
So with the fluid, it won't indent as much, so it'll be smaller, which, well, in that case would be actually, would say
It's a larger
higher
hardness.
load, but
Yeah.
higher hardness.
So that it's not a higher hardness. So
but yeah,
so I
You
think
see my question.
I understand your question. Right.
you know, it's-
So I understand your question. So one comment to that question would be, we use the Vickers hardness to explain that the hardness is decreasing. In the actual process of wire scribing or wire sawing, we cannot say a static hardness or whatever is happening during a indentation process is not happening in a wire sawing process. Right?
Yeah.
Because there are dynamic effects involved.
Yeah.
The liquid fluid film will have like some weird thing going on, versus when you're doing indentation. But I understand if it is actually indenting with what you're saying, the fluid taking more of the load, then it would create more hardness. It doesn't.
You know, and I was just, if I was doing this, what I would have said, if I got this sort of result, would say, okay, let's just put some, just water on it. Just
Right.
It's simple, something really simple. I know what that is. I don't know what's in this proprietary fluid. Do I get the same results, or do I get, different results because the fluid is actually making some changes to the surface?
Now,
Different fluids do different things.
yeah, like acetone and DI water and ethanol. Those are the three things Dr. Dan.
Yeah.
Viscosity differences are also.
So perhaps Dr. Danilov will explain everything, clarify.
But I think he raised some good questions.
Yeah,
I think that's probably something that needs to be
Okay.
addressed.
Okay.
No, go ahead. Go ahead.
I don't think,
Other questions?
I have nothing at the moment. That was,
I don't want to.
because I discussed this, I've met with Arkadeep quite a few times during the course of his work here. So we've discussed many of the other
Right.
things already. So.
I will always keep you updated. Yeah.
Yes,
Yeah.
okay.
Steve, so just to answer your question, Professor,
Yes.
there is a big difference between fluids and how they behave in an indentation experiment. And you measure it by the size of the indent, and then you measure the crack, the median crack distances. Unfortunately, I don't remember what the results were that we got back in the 80s.
Yeah.
We can look that up if I think.
Well, it's very intriguing, and so you almost like task 5 just gave us a teaser, like, oh wow, now I want to know more about what the influence of different fluids.
So we investigated this, and I mean, our explanation was it's an electrostatic effect. So you have sodium and chlorine ions, or sodium and potassium, or something like that. You get absorption on the surfaces. They basically create certain mechanical effects, electrostatic kinds of absorption processes. So I think that's the answer. But fundamentally, you don't really know the answer. I don't know the answer. The real fundamental reason.
I think that there is still some debate about whether this is effective.
Right.
So there are people who buy it, and there are people who don't buy it.
Yeah.
So I think it's a fair question to raise.
So
It's the explanation Arka's forwarded, and he's trying to kind of validate that assumption by measuring hardness, but I think there's some good points raised.
So the reason, I'll make one more comment about this, and we gotta get off this topic, but the reason we in my group never pursued this dislocation explanation is because dislocations are not active in silicon.
Room temperature.
You gotta get up to about 750 centigrade before dislocations actually are generated. Okay, so we didn't feel like we could sort of explain it by a plastic deformation process. It had to be some other process. That's really that's the way we interpret it.
But what do you have to say to that?
So we see plastic deformation happening in the ductile mode results, right? And that is happening because of one possibility is the electrostatic differences which the sodium and potassium ion is creating. But the plastic, because I mean, these are clear evidence that it's plastic, or even the Raman spectroscopy also shows it's plastic.
Why do you say that?
Because from the surface morphology, we don't see any cracks, whereas material is removed and there is no cracks.
But do you see dislocation emission? Do you see dislocations? Do you do any kind of dislocation etching to show that there was actually more dislocations?
So I remember your work, which annealed the silicon after raising it to high temperature using different scribes, and you found that dislocations are generated more if the fracture is less, because if the fracture has occurred, the energy is all gone, right? because fractured surfaces, the energy is going into the fracture. If the fracture doesn't occur, then only the energy is kept in dislocation. That's what the finding was from the Lim Danlup paper. Yeah.
Yeah. This is the one.
Yeah, so I understand the debate, but what Dr. Danlup pointed out was we are surely seeing softening either from the hardness measurement or from the surface morphology or from the Raman spectroscopy, because this is showing that it is ductile, not as big. Now, the reason it could be, as you're saying, that whether dislocations are moving because of the electrostatic or the zeta potential creating some change in the surface charges, that is one way of explaining by the reminders and Westwood effects.
But you cannot verify, you have not.
I have not
verified the fact that somehow there is greater mobility of dislocations in the presence of the fluid. I mean, that's what it would take to verify greater mobility of dislocations in silicon under loading, in this case. I mean, that's the difference between what Dr. Danlup said.
is saying.
You have loading,
I've loaded.
okay? At just pure room temperature, you won't, but under load,
Yeah.
sufficiently high stresses, you do produce this change in phase. But is that phase change connected with dislocation activation of some sort of greater mobility? That is an open question. I think you're better off acknowledging it's an open question than debating it.
I guess, as you pointed out, that we would never know. But in literature, we found that if you put a surface charge on silicon, the dislocations move differently versus like no charge at all, right? With zeta potential, there is surely a difference in the surface charge and the bulk, right? That's why we see a zeta potential. That is the electrostatic potential difference. So whenever we are putting a surface charge, that is same as putting, two wires on silicon, and that is it. We have seen in literature, like in electronics and others, that causes the surface charges causes dislocations to move differently. So because of the ionic liquid in contact with the silicon, which is the electronic material, we are providing this hypothesis that here also, because of the ionic liquid, it causes some surface charge, which causes the dislocations to move and make it softer. But you're right that we cannot. There might be the effect because the load is there.
You have not verified
the
dislocation.
I mean, I'm basing off this hypothesis based on the previous work of Westwood and Yost and Williams.
All right, like I said, we could go on for hours on this. But I want to make a point.
Yeah.
Okay, so I'll ask you a question to make a point. On the Raman spectrum for the diamond hardness, how confident are you that you can measure a 0.2 reciprocal weight number change between those two images?
So, so the resolution, Dr. Melcote had asked me this question earlier also.
I never even thought of it.
Right.
But you're making a big point of this, right? So you need to say, I have a lot of confidence in this change or not.
Mm-hmm. Right. So the resolution of the Raman spectroscopy is 0.6 or 0.5 centimeter inverse, and this is 2, not 0.2, but 2 centimeter inverse change. Now, I think we have done this debate earlier about Raman showing higher stresses compared to our polariscopy results. I mean, the whole point of this study was to find if graphitization is taking place. We found that graphitization did not take place because in some previous study, people had found graphitization when diamond wire sawing is taking place. But we found there is still a shift, and that could be because we went, only, let's say 320 millimeter. In the diamond wire sawing, it goes for kilometers with those pools of wire.
I'm talking about the 0.4.
Oh, okay. So, right. So, you're saying this 0.4 is significant or not?
So how do you believe it's significant?
I believe it's significant because this was done over many measurements and then taken the average and standard. We found it to be consistently giving higher for the multi-crystalline silicon case compared to monocrystalline silicon. And it's consistent with the story we have that the forces are higher and it is expected to create higher stresses. So it validated what we are seeing very readily earlier. Right? And it also validated, the radius of curvature change was more. So it was very consistent with the story which we found.
But again, the story is that some mechanism, some mechanical mechanism at the tip of the dime is causing, or is the cause of this. But that's only your prejudice, or your bias, not prejudice, your bias to having it come out somewhere. I'm just saying, you have to be, if you told me that your measurements are good to 0.01 reciprocal wavelengths,
One more, yeah.
fine, then I'll accept your explanation.
Yeah.
So that's the question. To what degree of accuracy will you stake your car on? You bet your car on that 0.4.
That's why I sold my car.
All right, anyway, think about that. I mean, I'm just,
That's a good point.
I saw, well, you gotta be pretty confident.
I'm not sure, I'm not sure you can defend necessarily the actual differences you're estimating in the residual stresses, because they are of the order of 0.4 per centimeter patient, Ramacha. But, if the question is how many repetitions were made, and, is there some way of showing that at least statistically these differences are present at some level of statistical confidence, and then saying, okay, there's an order of magnitude stress. Now, whether or not there is more stress in the tool that was used to cut multicrystalline silicon versus monosilicon, that I'm not sure with what degree of confidence you could say. So because you have a difference of only 0.44%.
Right. So on that note, you said about my bias, whether it's some mechanical thing happening in the tip. That is shown by the radius of curvature change to be more aggressive at a higher rate for the multicrystalline silicon tool. So there is something happening at the tip for multicrystalline silicon, which is making the tool rounder more compared to, this study is again the difference between mono and multi, because we want to answer the question why multi wears more, as that was the feedback given to us from our industrial collaborator. And so whatever differences we see may not be as significantly different. One can come and argue and say, oh, mono is also getting more, right? And that's true. In the previous task, we saw monocrystalline silicon wafers being cut by diamond, and diamond showed a lot of fracture. Like these are cut by monocrystalline silicon, right? These wires. So these are actual diamond on the wire. So monocrystalline silicon also wires the diamond. I'm just making the point here that multicrystalline silicon wires it more, or creates more forces, which is expected to create more stresses, residual stresses as well, applied stress as well as residual stress. And the radius of curvature of the tip is more rounder, or it's rounding more, blunting more when cutting multicrystalline compared to mono.
Would you say that if you had gone longer distance, some of that just 320 millimeters, would you expect that difference to grow, and maybe the confidence level of your conclusions about the residual stress in particular, right, to be greater? So maybe you have to couch. Yeah. Anyway, that's my question.
So on that note, I'll address that question, because 320 millimeter is very small distance compared to the actual distance moved by diamond wire sawing, which is kilometers. Like I think those spools are 50 kilometers. They can hold 50 kilometers of wire, which is huge. And so a wire or abrasive moves for many, many kilometers before it is taken off from the ingot. We have not gone that much. If at all we had got that much, it might have created graphitization. And there are prior work which showed, like the Yang et al. Work, which showed 2 out of 20 abrasives they had analyzed showed graphite. So they found also similar phase transformation along the same order of magnitude of like difference in residual stresses. So what I see here, I'm confident that it is showing a trend, but I acknowledge Dr. Melkote's comment that if we go longer, the trends might be more, what do you call it, more prominent. But the trend here is enough to answer the question that multi-extent silicon is more aggressive on diamond compared to mono.
All right, so I'll ask you one last question, but just to get your sense of things after doing all this work. So your thesis is sort of a mix of static and dynamic work. It's mainly static. It's mainly static. So what do you think about the dynamics and the real wearing and real cutting operation? What do you think is going to change here going forward with this work?
So I acknowledge the fact that I'm doing very low speed scribing experiments, and there would be an effect of speed, which is one of the part of a proposed future work. In the actual wire sawing process, it's moving at 10 to 15 meters per second, and I'm moving at less than 1/10 of that.
Huge difference.
Huge difference, and we know in cutting operations, the speed would affect in the amount of energy going into the process, might affect temperature. Here we're only talking about stresses, and I did not talk about temperature at all, because I found using empirical models, the temperature increase is not high, like not more than 100 degrees Celsius, which would not create any change on diamond. But with dynamic, I am expecting there will be more effect of like temperature and other things, which will create the wear more. But that would affect equally for both mono and multi. So the results here still would hold, but we have to take dynamics into account.
All right, thank you.
Chris?
Yeah, two general questions. One on the part orientation and cracking, and then the other on K1C measurements that you did. The first one was, can you go to slide 23? Just want to understand kind of what the relative orientations are here. And I think I might have asked this question during the proposal, if I remember right. So when you're cutting these wafers, what do you think is more important from a damage perspective? Is it the lateral cracks or the median cracks?
Right.
To the final performance, whatever it is. I think you reported flexural strength in one.
Fracture strength. So for fracture strength, the median cracks are more important. If you have median cracks, that is perpendicular to the surface. So if you bend a wafer, any crack which is perpendicular to the surface would open up and cause fracture. So median cracks are more important for a final perspective compared to lateral cracks. In fact, they mentioned that, so you see more lateral cracks on the new wafers, on the wafers cut by the new wire, and they are expected to chip out. And that's exactly same what we see on the surface morphology, more chipping. So the results are actually very consistent. That the surface shows more chipping, which is meaning there is more lateral cracks chipping out. And that's what we see in the subsurface, whereas the surface for used wire wafers does not show as much chipping because there are cracks which are deeper and median cracks.
So are we looking at the sidewall? Like I'm looking at, this is a nice figure actually. Am I looking at the flat surface of the
Side
cut?
I did have a picture of the curve which Dr. Daniluk had done a long time back in SEM. I have to see if it's in the back of the slide.
So wouldn't the median, like as you have described median cracks in this context, wouldn't that be along the sawing direction? So as you cleave through the wafer, wouldn't the lateral cracks be the ones that are left in the actual wafer itself?
So both are having.
That's a good question.
No, that's the curve question. Yeah.
Yes.
I have the curve somewhere.
Yeah. I think, we did talk about this.
Yeah. Okay, so the curve, as you are speaking, I should have put this curve back in the slide. So,
Yeah, go ahead.
yeah, so whenever abrasive is contacting with silicon, what we are seeing here is these wafers, the side walls of the curve. And let's see this abrasive, right? It creates median cracks as well as lateral cracks. The lateral cracks is chipping out. So if this becomes a wafer like this, the lateral cracks is chipping out, and the median cracks are perpendicular to the wall. So when you take a section,
So if you get to the deeper trenches, you're putting median cracks into the wall.
right. And what you're saying about the cutting operation here also, so that's what happened in the material removal here. That's the maximum material removal. That
Can
is
you move to the side, please?
Yeah. So here, the material is getting removed because of median cracks which are going here and cleaving, and lateral cracks is just removing the chips.
But what if the lateral crack right underneath the wire
Goes into
is
here.
big enough that it goes into the wafer?
So the wire size is 140 microns. The crack size is 10, 20, maximum is 40 microns I've measured. So half of 140 is 70, 80 microns. It won't go into the thing. But we did talk about this earlier.
That's very helpful. And just as a follow-up, what is the typical post-process after a sawing operation? Is there planarization that polish that out? These cracks are gone, or
So the typical process is etching with KOH to remove the damage, and the damage removal is as much the cracks depth, and the damage removal used to be around 40-50 microns earlier, but with recent advances in this abrasive shape with our manufacturer feedback, we found they now only remove 5 to 10 micron of damage by that chemical.
Okay, so it's getting on the order of the crack length
Yes.
that you're seeing.
Right.
But is there any guarantee that they remove all
All
of
the
that?
cracks, it's not guaranteed. So it's best to reduce cracking as much as possible. And cracking is a stochastic random fracture process. So there could be a crack, like I am investigating many, like let's say 25 locations, and I found maximum crack is 9 or 10 micron. But I might have missed a 10 or like 40 micron crack, which is there. And that could cause fracture later on.
One last question on slide, you go to 31.
Oh, sorry.
So you're reporting the scribing forces for both mono and polycrystalline silicon. For this, you reported higher forces for the microcrystalline silicon. I guess these were scribes that you did across this sample here, right?
Right.
And did you end up seeing any oscillations in the force when you're going over different grains, or because you talked about different K1C and
K1C,
I guess
that's
that's
right.
different strengths.
So here we are looking at the forces which are at 10 micron depth of cut, at which the fracture is brittle. That's why you can see on your eyes that the scribes, right? And that's if the fracture is brittle, those oscillations are confounded with any change in what you're saying in K1C. And also, these forces are over 20 millimeter, and in 20 millimeter, I'm encountering many grain and twin boundaries. Compared to the grain and twin boundary result you saw was over like 20 microns. So,
And tie this back to what you did before, if you happen to look at the, I guess you're going to encounter many grains.
Yeah.
So you'll come up with several different grain boundaries. If you happen to look at damage and cross that track, as you get to different grain boundaries, are you seeing the phenomena that you saw before of, as you get near a grain boundary, particular kind of grain boundary, the damage becomes restricted versus like a cracking becomes
right,
less
the cracking frequency changes.
Yeah, do you happen to see anything like that? Or?
Yeah, so the result you showed was representative. There was, I think in the thesis and the papers had more results which showed other grid shapes driving across the grain boundary, and it also showed distinct difference in the cracking frequency across the boundary.
But the question Dr. Saldana is asking is in this experiment,
In this
where you're
Did you see
actually
the same
doing
thing?
multi versus mono,
Right,
you're going 20 millimeters.
right.
Did you see a noticeable effect of different grains, the discontinuities you encounter? Do you see any evidence of that in
The
either
cracking
the
frequency.
morphology or the surface characteristics or in the forces? So
So
that's really what he's asking.
I see. So in this experiment, as I mentioned, the focus was on the wear of abrasive and not on the surface morphology of silicon.
You did take a look.
No, so the depth of cut was 10 microns, and at that depth, the fracture was pretty much consistent across all.
So the phenomena you're reporting before is at the lower.
At a 250 nanometer temperature.
Oh, okay. And the last question I had was, you reported different K1C values for those two grains across the twin boundary. Is it something that you measure in the bulk, or is it near the grain boundary? That you
It's near the grain boundary. So along the boundary I measured. I mean, it's not viewable here, so yeah, along the boundary.
It's right on
Right
side
on
of the
one
boundary.
side of the boundary and the other side of the boundary. And same
You
for
also
grain.
measured in the interior of the grain.
And they did not show as much difference.
Yeah, because the twin, they should be the same.
Same,
roughly, right?
roughly the same. They are not statistically as different compared to the differences in the vicinity of the boundary.
Has anyone reported why the K1Cs are very different for these materials near grain boundaries? Is it because of dislocation?
So
Pile
there
up
is
on
a-
boundaries, or is it because of? I think in your thesis you talked about just the
I did.
interface
Right.
being a natural.
So I did some experiments way back in 2012 when I started, and they are not in the thesis. And we found that dislocations, there is a K1C correlation with dislocation density. So dislocation density and K1C are interrelated. And K1C depends on dislocations, but in that study we only looked at dislocations, but there could be other things at the boundary, just discontinuities and like impurities or silicon carbide nitrate, which can affect the fracture toughness. But when you are just doing indent, we are not seeing what it is encountering. We're just seeing fracture toughness.
That's interesting. I mean, if nobody's reported it, it seems like
Yeah,
an
that's
interesting
it's
contribution.
a, well, there's some, we've done it.
We've done it.
Actually reported in
Yeah.
previous work. Never found as much, never received as much attention. So I don't know, maybe we were excited about it, but the fact that there is a correlation, because in all of these wafers, I mean, these are, even in the single crystal wafers, they have less crystal growth induced dislocation density, but there are some, and there is a distribution. You can do dislocation etching and show, and in the multi-crystalline silicon in particular, you have, even within the grain interiors, you have clusters where you see many more dislocations than others. And previous work done by Arka and others too, where we looked at both fracture toughness variations in those regions, as well as dislocation etching to identify those regions, and then use sister wafers to do dislocation measurements. You see differences both in the scribing behavior as well as in the fracture toughness. Of course, that's an empirical correlation, right? Yeah, but there is. Fine. Other questions? No? Okay. All right. So thank you, and so we'll excuse everybody but the committee. So you're excused as well.
Thank you. Should I turn that?
Just leave it there. Leave it there for
It's
now.
recording.
Huh? Yeah, leave it there. Leave it there. Do not turn anything off. Chris has to hear everything. He's the other committee member. Yeah.
Yeah. This was pretty interesting. The dislocation movement above something. That control.
No, we didn't do that.
Oh,
I
you saw it about.
I didn't think you saw the word. We never did.
Right.
All right, gentlemen. So, what do you, any concerns? I mean, just as a note, I've taken notes, the questions. So some of the interesting discussion we had on the last task. I think it behooves some attention being paid. Now, the paper's already published in Applied Physics Letters, so it's too late to change the paper. But at least in the thesis, I think some discussion and acknowledgement of other possible. And I think personally, if he can go and look at the indent depths when he did the indentation hardness measurements to see if the indent depths were any different. But they probably were, because he gets different C values, the crack length values. They were.
They'd have to be, because the
They'd have to-
inner
they'd have to
geometry was.
There have to be. So I don't know how you would prove, but maybe that's another potential source. That's I think a good point. I don't know. Although, unlike most other lubrication regimes where you have confined fluid, there is no confinement of the fluid. So if the indenter, this is my hypothesis, not his. If the indenter is actually going into the fluid can get pushed out much more easily. So there's nothing to build up pressure other than somehow trapping fluid. Whereas in a bearing, etc., you have you have confined fluid. So you're going to build up pressure and that will take up load. So I kind of buy the argument. However, I realize that this is debatable. So I will have him put some discussion that acknowledges other possibilities, maybe.
And I just brought it up
No, it's
because
good.
I'm not.
It's good. It's good. No, that's
the
the whole purpose.
mechanical thing.
No.
That goes beyond me.
We weren't either. We weren't either. This is asking the question, why we see what we see.
Yeah.
That led us down this path. I forced him down the path to go down and see. I remember Steve mentioning many years ago this chemomechanical effects. I said, okay, well, let's dig into this a little deeper. So I have made notes of that. I think some acknowledgement of that would make it a stronger dissertation, more honest dissertation.
And he could just mention, add a bullet in the recommendation
Yeah,
for future work.
That's
I
true.
think there's some,
That's true.
some unanswered questions.
Yeah. Of course.
Let me just also chime in. So my group back in the 80s,
Yes.
but what happened was, I was sort of coming back into my long-term memory, if you have water present during the process, whatever the process is, indentation, scribing, whatever it is, the hardness is not that different between water and no water, okay? But if you have alcohol-based fluids, acetone, or even acetone, or well, ethanol, certainly, acetone, trichloroethylene, or something, people try to relate it to carbon chain lengths that are related to this electrostatic effect. So then it becomes a bigger effect. So
There's absorption of these.
Yes. So here's the conundrum, you might say. So when we looked at this problem and we interacted with industry said, I'm not interested because I'm not going to put alcohol in my system or trichloroethylene. I'm not going to be doing it that way because of environmental effects and hazards. So there's a limited interest in it. Maybe from a fundamental scientific point of view, there's interest, but from a practical point of view, it would be very difficult to implement this.
Well, so it's true. But however, if so, this is the reason for looking at it as far as the material removal mode is concerned, is if indeed you can engineer the lubricants, if you understand enough about the lubricant constituent elements, then you might be able to promote a certain behavior, and then there is practical relevance.
Yeah, that's a knob you could turn to improve yield.
We don't know though. I think Steve has a lot more experience in this. This is,
We ran out of money. At some point.
Somebody. I'm just
Come
kidding.
to an end, you know.
Yes, of course.
Done.
But any other major burning concerns?
No, I thought he
went a little long.
He spent a little time on this, but he went in depth and really tried to understand everything, and I think a lot of the work makes a lot of sense. So, and
Chris?
Well, yeah, it's published well, so.
Yeah. But the last one's the wear stuff. The last one, diamond wear stuff, is just submitted to Journal of Applied Physics. We'll see what happens. But yeah, that's the one that's pending. So, okay, very good. Do you, as a committee, at least the people here, and this is being recorded, and probably his parents also watching. No, but nevertheless, Chris is going to have access to this, and he will see it, and he will provide his independent feedback. But question is whether you're comfortable signing. Okay, very good. So I will call him in.
Do we need the forms?
I'll ask him. I think he has something here. So
and then I probably need to go.
yes.
Yeah, I've
Of
got to
course,
get out
of
of
course.
here too.
Yeah, no problem. I'm not sure would.
I'm giving a final right now.
Oh, okay. I appreciate it then. Okay, so
Sit somewhere else.
so names are there. You just have to look at your name.
All right.
Let me call him in.
Okay. Yeah. How are you doing? I haven't seen you in a while.
Doing all right.
So, I will refrain from congratulating you yet, only because I think we still have another committee member. But the committee members here are happy with your work. And they've agreed to, and if you have any comments, yes, please give it to him and we'll make sure they get addressed. I have some notes and we'll talk about, how we might address some of the comments that came up. And that's it. And then I'll congratulate you after Chris is done. Okay, thank you very much. Yeah. Thanks a lot, Chris. Thanks, Rick.
Thank you.
Enjoy.
Okay. Yeah, turn it off.
That's what Mike did, right? Get started.
You wanted to stop it because your parents are also watching all this
Oh, yeah,
discussion?
they are actually watching, so they heard you maybe.
They probably heard.
Yes.
They heard us.
Okay.
Okay, keep it to yourself.
That's okay.
No mystery. You'll know what we said. I wanted it there because Chris needs to hear our
Oh,
discussion.
no, that's fine, that's fine.
Just to be fully, just transparent of the whole process. So. Okay.
Okay.
I thought the presentation was good. I think you did a nice job of explaining everything, except it went a little long. I was trying to get you to go a little faster.
Yes, I saw
You
that.
took a long time to get to research objectives.
Yeah.
I mean, it was nice. It's for the uninitiated, it's nice. Those who don't know much, for them, I thought it was very informative. However, when you're trying to present a thesis, you have to make some assumptions that the people you're really talking to are the people, the committee, most important, who of course have a quicker understanding. They can understand much quicker, faster. So you could have gone a little faster initially, but that's okay. I think all in all, I thought it was a very nice presentation. I think you demonstrated your knowledge and understanding. And Dr. New said he was happy. He said you dug deep. There's obviously questions about the chemomechanical stuff, and I thought he raised a very nice point, frankly, which we didn't discuss about. But I discussed. I told them. I said my hypothesis for that, unlike lubricant pressure buildup, which occurs in confined regions in bearings, it's confined fluid. There's nothing confined here. If you put an indenter, the fluid can be pushed aside, right? So there is nothing to build up pressure. Okay, so it's not confined region. So it's not confined fluid. So I think I buy this argument. But if there's some way, the only way, and I thought you did a nice job of explaining, saying, oh, look, there's evidence in literature where people actually looked at electron mobility, or dislocation mobility, kinks and a mobility of the kinks, where when you apply the potential difference. Now, if you're generating a potential difference, which the zero potential demonstrates, then the same thing should apply. Yeah. So I think that's a good answer. I think it's a good answer. I don't have too many major things. I do think we should have something, maybe in future work, he suggested maybe. But I thought maybe we'll have a more honest discussion in the chemomechanical side of I think the friction, you should mention. You should mention there that, one possible reason could be effect of friction, but we looked at the average coefficient of friction and they are not that different. That I think we should mention.